All right, section 3.5, we're just doing a kind of a quick video here. In 3.5, we're just looking at bringing in derivatives of the trig functions. And so there's a little box that has you go through. Let me see what page that's on. Has all them in a nice, concise little box on page 174. Okay, that just reminds you if you need if f of x equals sine x, okay, and then I'm just going to use a different letter over here, cosine x. All right, then f prime of x for sine equals, the derivative of sine equals cosine. The derivative of cosine equals negative the derivative of sine, okay? All right, and then they give you what happens if you have a tangent, then what happens if you have secant, and then over here, it's what happens if you have cotangent, and what happens if you have cosecant. So see how the functions that I'm doing on the left column are sine, tangent, secant. Okay. Then over here, I'm doing the cofunctions of those. And watch what happens when you do the derivatives. The derivatives are also cofunctions, just with a negative out in front. Okay, so if you know the derivative of tangent, then you can get the derivative of cotangent. So the derivative of tangent, I'm not proving them right now, is secant squared x. I'm not saying it's divided by. So let me get that line out of there so you're not thinking I'm saying that. Okay. So I just wanted you to observe that on the left side versus the right side, these are cofunctions. And that when you do the derivatives are cofunctions just with a negative in front on that side. Okay, so the derivative of tangent is secant squared x. So the derivative of cotangent is going to be negative cosecant squared x. The cofunction of what you saw over here, just with the negative out in front. And then same thing here. Okay. But the derivative of secant is secant x tangent x. So the derivative of cosecant x would be cosecant x cotangent x with a negative out in front. Okay. Now really, don't forget that tangent x is really sine over cosine. So if you forgot or don't know those, you could always go and use the quotient rule. Okay. Remember, secant is 1 over cosine. So you could use the quotient rule on those, couldn't you? And cotangent's really cosine over sine. So you could use the quotient rule there, and this is 1 over sine. Okay, let me write it right here so it matches. So like I'm not good at memorizing, don't like to memorize. So a lot of times I'll just go back to my trig and use what I know about that. So these are important to know. And then the others you can derive. All right, so that's all that's really going on in section 3.5. So that's not going to be a real hard section. Let's just do, let's see, where's some examples. Let's just look at a couple of those. So we're going to be able to, so far you know a lot of the basic rules, power rule and so on, and you know the product and quotient rules. So now we're just going to have some problems involving sine, cosine, product and quotient rules. So let's just pick a couple. So what about, let's do number 4. No, let's do number 5. On number 5, I've got y equals x squared cosine x sine x. Okay. All right. So let's see. So that's got to be a product rule problem. And you might want to split it up somehow because, your product rule really tells you what to do when you have two things. So it might help to just think of it as these two, where the first one actually needs to be split up again using the product rule. So first I'm thinking about the overall thing. So I'm going to do, for the product rule, I'm going to do the derivative of the first, which is going to be, when I do the derivative of the first, wow, okay, let me make sure I keep my bearings. Okay, so I'm doing the derivative of this right here. Okay, but when I do, it's got two pieces. So the derivative of this would be the derivative of the first times the second as is, plus the first times the derivative of the second. But now that's just the derivative of the first. Okay, so, I got to multiply that times sine x. Okay, then I need to take the first as is times the derivative of the second, which is just cosine x. All right, so that was a little tricky. So this was my first function. This was my second. And right here was d1 times the second plus d2, plus 1 times d2. But then when I did d1, I had to do the derivative of the inside first times the second part plus the first times the derivative of the second. So I really had to keep my bearings there. All right, so let me see now if there's anything I can do to clean this up a little bit. I think I'll go ahead and just put the sine x inside there. So this would be 2x cosine x sine x. And there's a minus here, so that'll still be minus sine minus x squared. So I'm doing these three multiplied together. So it'd be minus x squared sine x squared. And the way you write sine x all squared is sine squared x. Okay, so x squared, and then there's a negative, so that's where that is, sine squared x. Okay, so that's the first part. And then this, when I multiply, it's all times there, is just going to be x squared cosine squared x. Okay. All right. So at that point, I'm seeing an x that I can bring out. I hope we don't have to use a lot of identities from our trig classes to figure this out. I'm not really expecting you to remember a lot of identities. All right, so that really doesn't get that much better than that. You could factor out an x maybe and have 2 cosine x sine x minus x sine squared x plus x cosine squared x, but to me that doesn't make it look that much better, so I think this would be just fine. All right, now if this minus had been a plus, then I would have seen here that I could have taken an x squared out, and I had sine squared x plus cosine squared x, and if it had been a plus, I could have simplified that a whole lot more. Okay, so what's going to happen in 3.5 is you now have to use the basic derivatives of these trig functions within the context of a quotient rule or product rule problem at times. All right, so let's see. Let me do this one. This is number 12. Number 12 says, find y double prime, okay, and y was defined to be e to the x sine x, okay. So you're just going to do y prime first. So that's going to be the derivative of the first, which just happens to also be e to the x, times the second, plus the first as is times the derivative of the second, which is cosine x. Okay, so now you can factor out that e to the x, and you'll have sine x plus cosine x. Okay. And that may or may not make it easier because you're trying to do y double prime. So I was just kind of contemplating whether I'd rather do y double prime on the factored out form or this. I think it would be, easy either way. All right, so now when we do double prime, I'm going to do the derivative of the first, which is e to the x, times sine x plus cosine x. Then I'm going to take the first function as is and do the derivative of the second one, and it has two functions added, so I can do the derivative of each piece. So the derivative of sine is cosine, and the derivative of cosine is negative sine. Okay, so I get to there. Okay, and again, I've got the e to the x that I could factor out. So I'd have sine x plus cosine x plus cosine x minus sine x. So that does wind up simplifying a little bit because these cancel and these are like terms. So I have 2 cosine x with an e to the x. I think I'll squeeze the e to the x right in front of that. So 2 e to the x cosine x would be my second derivative. So when you're doing second derivatives, you just do the first derivative and then you go at it again, okay? All right, so you're not going to find this too bad. You just have to have what the derivatives for the trig functions are. You just gotta know those. All right, let's do one that may be a little messier, that involves maybe cosecants or tangents or something like that. Okay, let's see what this one turns out to look like. Let's do number 9 looks bad. Let's see what happens. Okay, number 9 was starting out with y being 8 tangent t over 9 plus 9 secant t. All right. So, and I just need the first derivative. All right. So I'm going to do low times the derivative of the high, which would be 8 secant squared t. Because remember the constant multiple rule, you can bring the 8 out and then do the derivative of tangent t. And the derivative of tangent is secant squared. Okay, so low derivative of the high minus the high times the derivative of the low, which has two parts. Derivative of 9 is going to be 0. The derivative of this would be 9, and then secant is a little weird. It's secant x tangent x. The derivative of secant is secant tangent. So secant t tangent t. Okay, so the derivative of 9 was 0. The derivative of this was 9 secant t tangent t. Okay, so now I'm looking, trying to see what I could factor out. Let's see. Could take out a secant, if that would help. I don't know that would help that much. Let's go ahead and pretty this up a little bit. Let me go ahead and just distribute this 8 secant squared t. So this would be 72 secant squared t plus 72 secant cubed t. Then this would be minus 72 secant t tangent squared t. Okay. All right. So I could factor out a 72 and a secant t. And what would be left would be a secant t plus a secant squared t minus a tangent squared t. All right, and this is where I sometimes worry that there may be maybe some identities or something that we could use that would wind up helping us to get that simplified so it turns out looking better than that. I'm not so sure. Oh, I forgot to do the 9 on the bottom. Forgot to do the low squared. I know that. I just forgot to bring it in. Let me bring that back in. The low squared. All right, so let me look, see if there's something better I could have done. Boy, sometimes I have trouble when it's a bunch of secants and tangents. I'm wondering if I could just change them into cosines and sines and then maybe see a little better what it would result in. Because I'm just not seeing it right here. Let me check one thing real quick. I'm just checking something to make sure. Okay, so there is a little something. I just wanted to be sure I had the signs right. So you remember how cosine squared x plus sine squared x equals 1? If I divide through by cosine squared x, then I have 1 plus tangent squared x equals secant squared x. And so if I subtract tangent squared x from both sides, that just reminds me that this is also an identity. Secant squared x minus tangent squared x would equal 1. So I was thinking that right there would be a 1. Okay. So right now I'm just afraid I haven't finished simplifying this. So I'm looking at some possibilities to see if I could do a little more. Okay. Well, that's basically secant plus 1. So that's like, okay. This is like 9 times 1 plus secant t. And then all of that was squared. So it's like I could knock out one of those. Oh, this is going to get us somewhere. Okay, so just bear with me. If this happens to you, I want to see what you plugged in. Did you use the quotient rule properly? Then go ahead and make an attempt at simplifying. So I was trying to do some simplifying. And if on trig functions, a lot of times I'll go back to sines and cosines rather than doing this business over here. But I just got to thinking, since it started with secants and tangents, I kind of wanted to keep those in there. So I thought that looked like a Pythagorean identity, and I just hadn't done it since last semester. I wanted to double check it. So at that point, I noticed down here, I really have 9 times the quantity 1 plus secant t. And that's the same as this. So one of those can go. So on top, I have 72 secant t times this secant t plus 1. On the bottom, I really have 9 squared, which is 81 times 1 plus secant t to the second power. So one of those can go, and I would just have 1 left. Okay, I shouldn't have put the x there. Let me do this again. So 1 plus secant t squared, one of those can go, and I just have 1 left down there. So let's see then. Then 9 would go into each of these, so that would be 8. That would be 9. So I'd have 8 secant t over 9 times 1 plus secant t. All right, I think that's it. think that's good enough. Okay, that's probably the hardest part, is knowing whether you're done, whether you've got it as simple as possible. Okay, so just work at it a little bit. Try to factor stuff out. Try to see if you can get things condensed as much as possible. All right, so that's probably enough of that. That's section 3.5. Now, when we do the chain rule, we'll be able to do the chain rule when it's involving exponential, polynomial, or radical or trig functions.